Hello guys, and welcome back to Introduction to Number Theory. This time we'll discuss another famous theorem that belongs to another famous mathematician whose contribution to number theory is really enormous. Well, I suppose you already know Euler, Leonhard Euler, and his theorem, Euler's theorem. But before we state the theorem itself, I would like to remind you that there is an Euler's function. We denote phi of n. It is the number of integers between 1 and n, actually including 1 and n, that are mutually prime with n. So this perpendicularity sign denotes mutually prime numbers. So k is mutually prime with n. We just count the number of such k's between 1 and n and denote this number as phi of n, Euler's function. So the theorem is the following. If we take n, an positive integer, and a, which is mutually prime with n, then a to the power of phi of n will be congruent to 1 modulo n. I bet you've seen something familiar before, something like this theorem. Well, indeed, if n is prime, then for every integer n, being mutually prime with n means actually not being divisible by n. And at the same time, Euler's function phi of n is equal to n minus 1 if n is prime, of course. So, combining these facts, we understand that Euler's theorem, in case n is prime, is just Fermat's small theorem. So Fermat's small theorem is just a particular case of Euler's theorem. And Euler's theorem is a generalization of Fermat's small theorem to all integer numbers n. Let's consider an example. Well, for instance, n equal to 12. It is not prime, so we cannot apply Fermat's small theorem to it. Let's try to apply Euler's theorem. First of all, we need to calculate Euler's function of n. So phi of n is, as we all know, we have a formula that allows us to calculate Euler's function, is equal to 12 multiplied by 1 minus 1 over first prime divisor multiplied by 1 minus 1 over second prime divisor, and so on. Well, 12 has only two prime divisors, so when we use this formula, we have only two pairs of parentheses, and it is equal to 4. So phi of 12 is equal to 4. Now consider numbers, integer numbers, that are mutually prime with 12. Well, we cannot consider all integers that are mutually prime with 12 because there are infinitely many such integers. Now we will consider only those that are less than 12. Well, we have 1, 5, 7, and 11. Only 4 integers less than 12 that are mutually prime with 12, which actually follows from the fact that phi of 12 is equal to 4. So these are all remainders mutually prime with 12. And let's raise all of them, each of them separately, to the power of 4 and see what happens. For instance, 1 to the power of 4 is equal to 1. Well, it is obviously congruent to 1 modulo 12. 5 to the power of 4 is 624 plus 1, and fortunately, or expectedly, 624 is divisible by 12, so 5 to the power of 4. So 5 to the power of 4 is congruent to 1 modulo 12. 7 to the power of 4, we once again see that it is something divisible by 12 plus 1, so is also congruent to 1 modulo 12. And finally, 11 to the power of 4, well, the same thing. It also satisfies the Euler's theorem and is also congruent to 1 modulo 12. What are possible proofs of Euler's theorem? Well, we have the first proof that involves group theory. And in order to conduct this proof, we consider a group of remainders, modulo n, but not all remainders, only those that are mutually prime with n. We denote this group by using the sign of multiplication or multiplicity. Well, this small sign that looks like x, well, it's not actually x, it's like a multiplication. So it's a multiplicative group of remainders, modulo n. And this group, of course, consists of exactly phi of n elements. So phi of n is the order of this group. As we know from the Lagrange theorem, the order of the group is divisible by order of any element of this group. Well, let me just remind you that order of an element is the smallest positive integer such that this element, a in our case, raised to the power order a, is equal to 1. So it is the smallest positive integer with this property. We know that order of group is divisible by order of any of its elements. So a to the power of phi of n is actually equal to a first raised to the power order of a and then raised to some other integer power. But since a to the power order of a is already 1, then this is actually 1 raised to some integer power and of course is equal to 1. Well, what does this equality mean? It means equality in the sense of group, of this group of reversible remainders modulo n. And if we were talking about integers, then this would mean being congruent to 1 modulo n. The second proof of Euler's theorem is elementary. We can consider all remainders mutually prime with n. Of course, the number, the amount of these remainders is exactly phi of n, and multiply all of them by a, and then just remember then when multiplying by a number mutually prime with n, we gain once again integers mutually prime with n, and actually the sets of remainders in the upper row and in the lower row are the same. Well, these are different integers, but they give the same remainders when divided by n. After understanding that, we can multiply all the remainders in the upper row and all the integers in the lower row and conclude that we gain two integers that are actually congruent modulo n. From this point, all we need to do is to simplify this congruence by cancellation. We simply divide it by the product of these r1, r2, and so on. And what we have left, we have a to the power of phi of n on the right-hand side, and of course 1 on the left-hand side. So this is also a way to prove Euler's theorem.